And we're off. Let's talk some more quantum physics. I call today's lesson straight up Twilight Zone shit. The previous video I made on this was on the uncertainty principle, which I still have up on the board because it's going to be applicable. It's got 4 views right now. If you're watching this, I would advise you to watch out one first. This is going to make a little bit more sense. I mean, you'll still be able to get the gist of this. If you don't understand it, it's pretty cool. I explain what the uncertainty principle is in pretty simple terms, I think. And then we perform an experiment to demonstrate it. I would recommend, if you're watching this, if you're interested in this, go back and watch that one. But it's up to you. You can still be able to understand this, I think. Yeah, this is some straight up Twilight Zone shit. We're going to talk a little bit about something called quantum entanglement, which Einstein called spooky action at a distance, and which I call straight up Twilight Zone shit. Really, I'm referring to basically all of quantum physics, though, with that, because a lot of this shit is unreal. Quantum entanglement, to give you a basic overview, is you've got 2 particles that are entangled. They can be separated by any amount of distance. My nose is itching today. They can be separated by any amount of distance. You put one on one side of the universe and one on the opposite end of the universe. And the thing is, the diameter of the observable universe is something like 92 billion light years. And however many light years away you are, that's how much it will take light. That's how much time it'll take light to reach that location. The nearest star here is the Alpha Centauri system, and it's like 4.25 light years away. It's actually 3 stars. 4.25 light years away. 4 years and 3 months. If I'm here and you're on a planet around Proxima Centauri, which is the closest star in that system, I'm here, you're on Proxima Centauri. If I send a message to you, the soonest you can get that message is in 4 years and 3 months. And it's another 4 years and 3 months if you're sending a message back to me. When you look at the stars in the sky at night, if you look at Alpha Centauri, you are looking 4 years and 3 months into the past. You're looking at it as it looked 4 years and 3 months ago. It doesn't matter if you're looking at it through a telescope, it's just a clearer image. It's the same length of time. Because in order to see it, the photons have to travel from that star to your eyeball, 4.25 light years away. And that's the shortest amount of time that we know of that distance can be traversed. So, in order for these 2 particles that we've separated, these 2 entangled particles that we've separated by the diameter of the observable universe, to send information back and forth to each other, for one to send any information to the other, would take some 90 billion years. I don't know exactly what the diameter is, but we'll round it off to 90, because it really doesn't matter. It would take 90 billion years for one to send any information to the other. There's no other way. They are not capable of interacting any quicker than that. And yet, the science has shown that if we were to measure one, if we were to measure a property of one, the corresponding property of the other would be determined instantaneously. That should be impossible. Okay, and Einstein didn't like quantum mechanics. He, referring to quantum physics, said, excuse me, Last video I made, I had sinus problem. I just had another sinus problem. Sorry about that. Einstein said about quantum physics, I believe that the moon is still there even when I'm not looking at it. Because there are some interpretations of quantum physics that suggest maybe it's not. There are some like very specific theories that are no more likely than any of the other many theories. So I mean, for the most part, it's there when when you're not looking at it. But the implication, and especially when you get down to the like small particles, as we demonstrated in the last video, that is very small. When you get down to something that small, this starts to matter, and properties become not so well defined. So Einstein, in order to explain the concept, the quantum entanglement, which it seems has these two particles communicating with each other instantaneously over a distance that should take a minimum of 90 billion years to communicate with each other, he suggested, well, maybe it's like a pair of gloves. Like you have a pair of gloves, you have a right glove and a left glove, and you could take that pair of gloves and put them in two separate boxes and not look at which one's in which box, and take one box around the world, open it up and look at that box, and you see a right-handed glove in that box, then you know that the left-handed glove must be in the other box. The other box must contain the other glove. But the weird thing is, it turns out he was wrong, and these particles really were making that determination in that instant. And we're going to kind of explore how we know that. Oh man, I'm going to edit this video. Sorry, I had to take care of something briefly. I'm going to edit this, so that's just going to look like a quick jump in the video. What I'm going to explain to you now is we're going to explore how we know that to be the case, that in an instance such as that, these two particles really are making that determination simultaneously and across that distance in an instant. And I'm going to explain this using an analogy. So just know that it is an analogy. I hope that's pretty clear, because I could stand here and I thought about like what to use as an analogy and how to do this and make it understandable and hopefully entertaining, at least to some degree. Because I could stand here and talk to you about electrons and photons and angular momentum and polarization, and I would lose 90% of you in the terminology. It's just not a good way to explain it. So I'm going to use an analogy, and we're going to pretend there's a place called Quantum World, where things as large as you and I behave as quantum particles. So just understand that this is an analogy. I want you to imagine we're in Quantum World, and we've got a tunnel. Okay? And on that tunnel, we've got a barrier at the entrance and a barrier at the exit. Clear enough so far? And there's no, this isn't like a brain teaser, okay, because it's going to start sounding like one, and it isn't. There's no like tricks here. We've got people standing outside this tunnel. I don't know how well you can see my master artwork here. We've got people standing outside the tunnel, and we're going to send them in that direction to the tunnel. At this barrier, we've got a door, okay? And we're going to use like substitutions for properties of quantum particles. I'm going to use hair color and eye color. And what I need you to understand about this is these are binary properties, okay? Which means we're dealing with one or the other, two states. So when I say eye color, we're not going to acknowledge like the full range of, you know, you've got brown eyes, blue eyes, green eyes. No, we're just dealing with, are your eyes brown or not brown? Simple. Hair color, we're going to go with, are you blonde or not blonde? Very simple. Only works if we're talking about binary properties. So we're going to send people to the tunnel. At the entrance, we've got a door. And that door will only let you through if your eyes are not brown. Okay, so like I'm fucked. I get turned away right at the entrance. We're going to be with a line over it. We're going to say that this door is only going to let you in if your eyes are not brown. And we're, again, not a riddle, not a brain teaser. We're not like imagining some situation where, you know, you've got like colored contacts or something, or you've got hair dye and you can change. No, you've got, your eyes are the color they are, your hair is the color it is. That's it. No one's walking around the tunnel either. You can only go in, through the tunnel, and out. That's it. So we've got a tunnel, we've got people outside the tunnel, we're sending them toward the tunnel. If they have brown eyes, they can't get in. If they do not have brown eyes, they're allowed to pass. People aren't going in like two at a time or something, one person at a time. If you have brown eyes, get out. If you don't have brown eyes, you can enter. At the other end of the tunnel, we have another door. This door, however, will only let you pass if you do have brown eyes. So anyone who doesn't have brown eyes has to turn back and come back out. What can we say about this? We can say, we should be able to say, for certain, nobody's coming out this end, right? No one's coming out here. If you have brown eyes, you can't get in. If you don't have brown eyes, you can't get out. No one's exiting that tunnel. And indeed, if we perform this experiment, or, you know, the proper analogy in quantum physics, that is what we find. Nobody's coming out. Okay, so far everything makes sense, right? Well, let's say we install in the middle of this tunnel. Now we install another barrier with a door inside the tunnel. And this barrier will only let you pass if you have blonde hair. That shouldn't affect anything here, right? Think about it. You have brown eyes, you can't get in. If you have blonde hair, you can pass, and if you don't, you can't. But that shouldn't matter. Because if you have brown eyes, you couldn't get in, and this still won't let you pass if you don't have brown eyes. But if you have blonde hair, you can pass through the middle of the tunnel, and if you don't, you have to turn back. So this should not be affected. Still, nobody should be getting out. Because what the fuck does hair color have to do with whether or not you have brown eyes, right? So, how fucking shocked would you be to have this experiment set up like this, and after installing that barrier, you start seeing people come out of the tunnel? with brown eyes. After installing that barrier, before they weren't. No one was coming out. You install the barrier that checks their hair color and allows them to pass if they're blonde. And at the other end of that tunnel, people start coming out. How did that happen? And the answer is, as it has to be, something about checking the color of their hair changed the color of their eyes. More precisely, if we're, again, talking about the analogy here, as it pertains to this situation, they didn't have a hair color or an eye color to begin with. Their hair color and eye color were in what we call a superposition, which is something that we can't really conceive of. It's both, neither, all at the same time. It's like this, it's what's called a wave function that represents all possible states. So before they got to here, they didn't have a hair color or an eye color. Both were superpositions representing a 50% chance of having brown eyes and a 50% chance of not having brown eyes and a 50% chance of being blonde and a 50% chance of not being blonde. When they passed through the first door, they received an eye color. Their eye color was determined at that moment. The act of observation collapsed that wave function and forced their eyes to become one or the other, brown or not brown. And in fact, 50% of their eyes became brown, and the other 50% became not brown. And so they went on. And they got to this barrier here, which checked their hair color, which again had no value. Had nothing up to this point. They did not have a hair color. It was in a superposition. The act of observation collapsed that superposition and forced their 50% of them became blonde, the other 50% became not blonde. But think back to the uncertainty principle and assume that these properties are related in a similar manner to position and momentum. Observing the individual's hair color caused uncertainty in their eye color, at which point their eye color more or less it reverted to a superposition, and could be defined again. Still with the sinuses. It could be defined again by making another observation. And it was defined according to the original parameters, which means they went back to not having an eye color, which means they didn't have a defined eye color to begin with. It was determined at the moment of observation. That's the only way this can work. If these people had an eye color to begin with that was set, then you still wouldn't get people coming out of here because it wouldn't have changed. By detecting the color of their hair we triggered uncertainty, in a sense, in the color of their eyes. And so what we knew about them, here was nothing. Here was both hair color and eye color were in a superposition. After they go through here, we know that 100% of the people approaching this barrier did not have brown eyes. But after they pass through here, because we're not allowed to know both, because they're related in a manner similar to this, we're not allowed to know both. When they pass through this barrier, your intuition says at this point you would know that they do not have brown eyes and they do have blonde hair. But that's not the case. Now, after they pass this barrier, you know they have blonde hair, but you don't know their eye color anymore. And it's not that you don't know their eye color, it's that they don't have one. It's in a superposition. And when they reach this barrier, their eye color is determined again, just as it was originally. And so 50% of them, remember, we're dealing with, let's say about, again, going by the analogy, 50% of the people who approach this barrier got through and do not have brown eyes, and 50% of the people who approach this barrier have blonde hair. So we're dealing with a fraction of the original number. And by the way, if you're just measuring eye color, once you measure that, until you measure something else that adjusts it in such a way, that's set. If you measure an individual's eye color, angular momentum along a particular axis, see why I used eye color instead? That's boring, isn't it? If you measure a person's eye color, and their eyes are brown, you can measure them 1 billion more times. As many times as you are, again and again and again. Just keep measuring. You can measure their eye color billions and billions of times every single time. It's going to be brown. Never. It never changes. Once you measure their hair color, the eye color is done. You can't know that anymore, and it doesn't have a defined state anymore. And that is how we get to that point. Some of their eyes now are brown, even though they weren't going in. What we're talking about in actuality is polarization of light or the angular momentum of electrons. And you can verify this if you get 3 polarizing filters that are designed to filter out polarized light. You can adjust 2 of them at 90 degrees to each other, and they will block out all light. No light will be able to pass through. You insert a third one between those 2 and adjust it to, I believe it's halfway between. It's 45 degrees. And for some, suddenly, again, due to this same concept, it's the same thing basically that's going on here, but with photons. You insert a third lens in between them, and now all of a sudden, light that couldn't make it through 2 is going through all 3. So there's that. And quantum entanglement is, again, if you got two quantum particles entangled, you could separate them by any distance. And no matter that distance, when you measure one and determine a given property, its angular momentum along a certain axis, its entangled partner will instantly assume the opposite orientation. Spooky action at a distance. Straight up Twilight Zone shit indeed. I believe that about covers it.